All right, so today we are going to continue talking about three-phase circuit analysis by developing some transformations that we can use to make any possible three-phase circuit look like a YY circuit. So let's first consider transformation between balanced sources. So on the left-hand side, I am going to draw a Y-connected source. And let's see, let's call this terminal A, B, C, and over here, this will be terminal N. I'm not explicitly drawing a neutral conductor here since our delta connected source will not have a neutral conductor to speak of. It's entirely irrelevant. This voltage will be VAN. This is VBN, and this is VCN. And over here on the right, I'm going to draw a delta connected three-phase source. Where we have terminal A, B, C. I'm going to make that C look more like a C so that it's clear. This voltage is VAB. This voltage is VBC. And this voltage is VCA. And our goal here is simply to figure out the rules that make these two circuits equivalent, okay? If we can figure out what that is, then we can develop a transformation from that. So how we're going to approach this is we're going to look at the voltage drop between our transmission line terminals and set them equal to each other. So effectively, VAB, let me write these line voltages here. This line voltage VAB needs to be equal to this line voltage VAB in order for these circuits to be electrically equivalent. Well, on the right-hand side, our line voltage is literally just our three-phase voltage, our delta connected voltage, VAB. And on the left-hand side, our voltage VAB is equal to VAN minus VBN. Okay. And I got that by performing Kirchhoff's voltage law around this loop. Okay. Since our sources are balanced, we know that VAN and VBN are related. So we could express this as VAN minus VAN times 1 angle negative 120 degrees, or VAN times 1 angle 0 degrees minus 1 angle negative 120 degrees, which is simply VAN times the square root of 3 angle positive 30 degrees. So effectively, if we want to go from a Y-connected source to a delta-connected source, we simply multiply by a factor of square root of 3 angle 30 degrees, right? So the A phase of our Y-connected source, or excuse me, so the A phase of our delta-connected source is simply the A phase of our Y-connected source multiplied by root 3 angle 30. The B phase of our delta-connected source is simply the B phase of our Y-connected source multiplied by root 3 angle 30 degrees, and it works for the C phase as well. So it shouldn't be wildly shocking to figure out that we can go the opposite direction, go from a delta connected source to an electrically equivalent Y connected source by dividing by 1 over root 3 angle 30 degrees. And so this is our simple transformation, okay? We can go from a delta connected source to a Y connected source by dividing all of our phase voltages by square root of 3 angle 30 degrees, and that will give us our Y connected phase voltages. So that transformation is pretty easy and pretty straightforward. Are there any questions on it before we move along to transforming between balanced sources, or excuse me, balanced loads? All righty. So we're going to do something similar here. Now, I do want to point something out. I am very specifically going to develop a transformation between unbalanced loads first, and then we are going to figure out how that simplifies when our loads are balanced. So we're going to start with a Y-connected load on the left-hand side. So here's terminal A. Then here is impedance ZYA. Here's terminal B. And our impedance ZYB. Here's terminal C. And our impedance ZYC. And our neutral conductor. And over here on the right-hand side, here's terminal A. Our impedance Z delta A. Terminal B. Our impedance Z delta B. Terminal C. And our impedance Z delta C, like so. So on the left-hand side, the impedance seen between terminals A and B is simply ZYA plus ZYB. And the impedance seen between terminals A and B on the right-hand side is going to be Z delta A in parallel with Z delta B in series with Z delta C, which we could rewrite as Z delta A times Z delta B plus Z delta C divided by Z delta A plus Z delta B plus Z delta C. So I believe the impedance on the left-hand side is very, very easy to see. The impedance on the right-hand side is a little bit more difficult to see. So does anybody have any questions or problems about the way that I have expressed it? All right, so what we are going to do is we are going to make these two impedances equal to each other. And then that's how we're going to figure out our transformation. So we could say from here that ZYA plus ZYB is equal to Z delta A times Z delta B plus Z delta C over Z delta A plus Z delta B plus Z delta C. Similarly, the impedance between our B and C terminals and setting them equal is going to look like ZYB plus ZYC is equal to Z delta B times Z delta A plus Z delta C over Z delta A plus Z delta B plus Z delta C. And the impedance seen between these C and A terminals is going to look like ZYC plus ZYA is equal to Z delta C times Z delta A plus Z delta B over Z delta A plus Z delta B plus Z delta C. So we have a system here. And this system can be thought of as a 3-equation, 3 unknown system in 2 ways, right? So if we know what impedances ZYA, ZYB, and ZYC are, we can solve for impedances Z delta A, Z delta B, and Z delta C using these 3 equations. Similarly, if we know what impedances Z delta A, Z delta B, and Z delta C are, we can solve for what impedances ZYA, ZYB, and ZYC are. So we can develop 2 different transformations from this, a Y to delta transformation, where ZYA, ZYB, and ZYC are known, and a delta to Y transformation, where Z delta A, Z delta B, and Z delta C are known. So let's start with the Y to delta transformation. And I'm put here ZYA, ZYB, ZYC are known. So if we solve our system of 3 equations where we're considering ZYA, ZYB, and ZYC to be known quantities, what we will find is that Z delta A is equal to ZYA times ZYB plus ZYB times ZYC plus ZYC ZYA all over ZYA. And then Z delta B is going to be effectively the exact same expression, except we just changed the denominator to ZYB. Okay, so it's ZYA, ZYB plus ZYB, ZYC plus ZYC, ZYA all over ZYB. And then finally, Z delta C, ZYA, ZYB plus ZYB, ZYC plus ZYC, ZYA all over ZYC. Now, let's look at what happens for a balanced system. Okay. So for a balanced system, where ZYA is equal to ZYB is equal to ZYC, we'll find that we have a single impedance Z delta that is going to be ZY squared plus ZY squared plus ZY squared all over ZY, which is simply 3 ZY squared over ZY or 3 ZY. So for a balanced three-phase system to go from a Y connected load to a delta connected load, we simply multiply the impedance by a factor of 3. So I'm going to come back up here, and our transformation in this direction is literally Z delta is equal to 3 ZY. If we want to go for a delta Y transformation, where Z delta A, Z delta B, and Z delta C are known, solving our system of equations gives us the following results. ZYA is equal to Z delta A, Z delta C divided by Z delta A plus Z delta B plus Z delta C. ZYB is given by Z delta A, Z delta B over Z delta A plus Z delta B plus Z delta C. And ZYC is given by Z delta B, Z delta C over Z delta A plus Z delta B plus Z delta C. For a balanced load where Z delta A is equal to Z delta B is equal to Z delta C, we'll wind up with a balanced Y-connected load where ZY is simply Z delta squared over Z delta plus Z delta plus Z delta, which is the same as Z delta squared over 3 Z delta, or 1/3 Z delta. So to go from delta to Y, we simply divide by 3 for a balanced. So ZY is equal to 1/3 Z delta. So these transformations are pretty easy to remember because they are equal and opposite, right? Let's scroll up here. So for our transformation between balanced sources, if we want to go from Y to delta, we multiply by √3 angle 30 degrees. If we want to go from delta to Y, we divide by √3 angle 30 degrees. For our loads, if we want to go from Y to delta, we multiply by a factor of 3. And for if we want to go from delta to Y, we divide by a factor of 3. So let's put this knowledge to use. We're going to work a couple of example problems here. So our goal is to analyze the following in a balanced 3-phase delta Y system. The source has ABC, or positive phase sequence. The line impedance is ZW is equal to 0.1 plus J 0.1 ohms. And the load impedance per phase is ZY is equal to 10 plus J4 ohms. That ohm signal symbol does not look good. If the line voltages at the source are VAB is equal to 208 angle 0 degrees volts RMS, calculate the line voltages at the load. So I'm going to draw our system. Since this is a delta Y system, that means the source is a delta connected source. and the load is a Y connected load. So I'm going to start with my delta connected source over here. Sorry, that should be the negative polarity terminal for VCA. Here's our positive polarity terminal, VAB. Here is our voltage source, VBC. And I'm going to draw my transmission line terminals here. So this is lowercase a because it's on the source side, lowercase b, and lowercase c. I do have a transmission line impedance. So I'm going to go ahead and put in my transmission line right here. So this is ZW. ZW. And ZW like so. And now I'm going to draw my Y connected load. What we were given in the problem statement is that VAB is equal to 208 angle 0 degrees volts RMS. ZW is 0.1 plus J 0.1 ohms. And ZY is equal to 10 plus J4 ohms. What we are trying to find is this line voltage, VAB. And once we know VAB, we can simply shift it by negative 120 degrees to get VBC, and shift VBC by negative 120 degrees to get VCA, and we'll be finished with the problem. So since this is a delta Y system, in order for us to use our single phase equivalent circuit, we need to transform our delta source to a Y source. We're not going to physically write out the full source or anything like that. We're just going to do the math. So we know that the A phase of our Y connected source should be the A phase of our delta connected source divided by square root of 3 angle 30 degrees. This comes out as 208 angle 0 degrees volts RMS over root 3 angle 30 degrees, which looks like 120.089 angle negative 30 degrees volts RMS. And that's just the math behind the transformation that we developed. Okay. From here, our single phase equivalent circuit is this. So here's A. Here's lowercase n. Here's VAN. Here's ZW and uppercase A. Here's ZY, uppercase N. And and we connect our neutrals with a short circuit. Now, one thing that I want to note here is that the voltage that we're looking for, VAB, is not able to be directly solved for in our single phase equivalent circuit. However, this phase voltage, VAN, and this phase voltage, VBN, could be solved for using single phase equivalent circuits. And we could just write a Kirchhoff's voltage law loop around this equation, or effectively we could just use the transformation to go from a Y connected phase voltage to a delta connected phase voltage, which is the exact same transformation that we used right here. Okay, it's effectively the same thing. If we want the transformation that we developed happens to work for converting a delta connected source into a Y connected source, but what it's really doing is transforming a delta connected phase voltage into a Y connected phase voltage and vice versa. Okay. So here's the voltage VAN. Using simple voltage division, we can see that VAN is going to be V lowercase an times ZY over ZW plus ZY. And if we substitute in our numbers, what we wind up getting here is 118.655 angle negative 30.293 degrees volts RMS, and VAB, excuse me, VBN is VAN times 1 angle negative 120 degrees. So this is going to be 118.655 with an angle of negative 150.293 degrees volts RMS. And from here, our line voltage VAB could be thought of as VAN minus VBN, which would give us 205.517 angle negative 0.293 degrees volts RMS. That's if we use KVL around this loop, or we could say that VAB is just VAN times √3 angle 30 degrees, which will also give us 205.517 angle negative 0.293 degrees. So we can do the work behind the transformation that we developed, or we can simply apply the transformation and we will get the exact same result. Okay. From here, VBC, simply VAB times 1 angle negative 120 degrees, which is 205.517 angle negative 120.293 degrees volts RMS. And VCA is just VAB times 1 angle negative 240 degrees, would be 205.517 angle negative 240 0.293 degrees volts RMS. All right, so this was an example, I believe a fairly straightforward example of using our transformations to get our single phase equivalent circuit and then effectively solving for a quantity that can be solved for using our single phase equivalent circuit, and then transforming that into something that we needed whenever our end quantity of interest is something that can't be gleaned directly from our single phase equivalent circuit. Let's take this one step further and look at a more complicated circuit, okay? The problem statement here is aggressively long, so I don't want to write the problem statement down. I'll present it to you as an actual circuit that we are going to analyze with some specifications. So in this circuit, we are going to have a Y-connected source like so. I'm going to list this as A, B, and C. We are going to have some transmission line impedance to take into account. And then we are going to have a load, which consists of two balanced three-phase impedances that are connected in parallel. We are going to have a delta connected load, and a Y-connected load. So I'm going to show you how you could represent that in a schematic diagram. This is effectively the hardest type of circuit I could possibly ask you to solve for. And the reason why I say that is because if we had two Y-connected loads in parallel, we could just represent them as a single Y-connected load by just giving an equivalent impedance. Similar, if we had two delta connected loads in parallel, we could just combine the per phase impedances, just using simple impedance combination techniques. So we can really represent any combination of Y connected loads and delta connected loads together using this circuit. So this point right here is going to be my neutral. And then here is ZY. Here is another ZY. And then here is our third ZY. So this is a delta connected load in parallel with a Y connected load, where our delta connected loads occur between A and B and C and A, and our Y connected portions are connected between A and N, B and N, and C and N. Okay. All right, so what are we told? We know that our phase voltages at the source are 120 angle 20 degrees volts RMS. we know that our Y connected impedances are 8 plus J2 ohms. We know that our delta connected impedances are 12 plus J3 ohms. And we know that our transmission line impedance ZW is 0.1 plus J 0.08 ohms. What we want to find is all of the line currents and then all of the phase currents in our load. Okay, so I'm going to represent only the A phase of our quantities of interest here for now. We might have to add some things later. So this current, IAA, is representative of the line currents that we're looking for. This current, IAB, is representative of the phase currents in our delta connected load. And this current, IAN, is representative of our phase currents in our Y connected load. In order to represent this circuit using a single phase equivalent, we are going to need to convert our delta load into a Y load. So I'm going to call our converted impedance Z delta Y. And this is going to be simply Z delta over, excuse me, I don't know why I put ZY there because that should be 3, which looks like 12 plus J3 ohms over 3, or 4 plus J1 ohms. From this, our single phase equivalent circuit could be drawn like so. Here is our A phase source voltage, VAN. Here's our transmission line impedance connecting our source to our load. Then we're going to have ZY. And in parallel with ZY, we are going to have Z delta Y. Our single phase equivalent circuit can be used to determine our line current IAA and our phase current IAN. It cannot be used to determine our phase current IAB because we don't have a B here in our single phase equivalent circuit, okay? But if we know IAA and we know IAN, this is actually all the information that we'll need to figure out that last phase current IAB, and we'll actually have 2 different ways that we could think about it, okay? So let's start by determining these 2 quantities. So IAA is just going to be VAN over ZW plus ZY in parallel with Z delta Y, which looks like ZY times Z delta Y over ZY plus Z delta Y. If I substitute in my numbers, I'll get a line current of 41.875 angle 4.897 degrees amps RMS. I can now use, and this was just Ohm's law, I can now use current division to find IAN. So I capital A capital N is going to be IAA times 1 over ZY divided by 1 over ZY plus 1 over Z delta Y. Because that whole current IAA flows through impedance ZW and then splits between those two parallel impedances. If I substitute in numbers here, I find out that IAN is equal to 13.958 with an angle of 4.897 degrees. So now we need to figure out what IAB is. So we're going to scroll back up here and think about things that we could do, okay? So one way that we could approach this would be figure out what this voltage VAB is, and then use VAB divided by Z delta will give us the current IAB that we're looking for. So that is one possibility. And actually, let's go ahead and do that really quick, okay? So we could say that the voltage drop over ZY is simply VAN, which we can solve for using Ohm's law. And then we could perform a transformation on our phase voltage VAN to make it a line voltage VAB. So that would look like this, okay? So we could say that VAN is simply IAN, which we solved for a moment ago, times ZY which comes out to be 115.104 angle 18.933 degrees volts RMS. From here, our line voltage VAB must be VAN multiplied by √3 angle 30 degrees, which in turn gives us 199.366 angle 48.933 degrees. Let me make this more obvious that that is a 4 volts RMS. And therefore, our phase current IAB, and let me make that look more like an A and not like a delta, is simply VAB over Z delta, which comes out to be 16.118 angle 34.897 degrees amps RMS. So that's one way that we could solve for that phase current IAB that we're looking for based on the results of our single phase equivalent circuit analysis. Let's look at a slightly different way. Okay. So we are going to have a phase current ICA that's flowing up into this node. So if we apply Kirchhoff's current law at this node right here, we'll have IAA and ICA flowing in, IAB and IAN flowing out. So it looks like we have two currents flowing in, two currents flowing out, but we only know two of those four currents. However, we also know that IAB and ICA are related to each other because this is a balanced three-phase system. So I'm going to walk you through the math that would be involved in solving for our phase currents through our delta connected load here using KCL. So IAA plus ICA, let's do that down here. Will be equal to IAB plus IAN. I'm going to move my known quantities to the left-hand side. So that means I'm going to have IAA minus IAN is equal to IAB minus ICA. I can express ICA in terms of IAB. So since ICA is the C phase, I'm going to have IAB multiplied by 1 angle negative 240 degrees, because the C phase lags the A phase by 240 degrees. And so this is going to look like IAB times 1 angle 0 degrees minus 1 angle negative 30 degrees, which is simply IAB times a factor of the square root of 3 negative 30 degrees. Okay. Sorry. This right here should be 240. I got ahead of myself. My apologies. So from this, using a little bit of algebra, we can see that IAB is simply IAA minus IAN over root 3 angle negative 30 degrees. And if we substitute in our numbers, we get 16.118 angle 34.897 degrees amps RMS. Literally the exact same number that we got using a KVL relationship a moment ago, right? So it really doesn't matter what way we pursue figuring out this last quantity right here that can't be solved for using our single phase equivalent circuit. But as long as we can apply basic circuit analysis techniques like Kirchhoff's voltage law or Kirchhoff's current law, we can always figure out what one of those quantities that can't be solved for using our single phase circuit is, using the results of our single phase circuit analysis. So this is what makes the single phase equivalent circuit in a balanced system so powerful, because we can get enough pieces of information to be able to solve for anything we could possibly want just using KCL, KVL, and Ohm's law. All right, that is enough talking for me for today. You have 2 homework assignments effectively over this material. I think it's homework number 15 and homework number 16. What we are going to be talking about next week is power analysis of 3-phase systems, which honestly, I could probably wrap up in one day, and then we could spend one more day working problems. But if you have any questions on any of the homework assignments or anything like that, I'd be happy to spend some class time talking about that stuff, because I understand that at first, this analysis can be rather confusing. So if you have a question about the homework assignments or anything that I've done, I'm very happy to answer it. If not, we will move on into 3-phase power analysis. So I don't have anything else to talk about today, so I hope you guys have a great weekend, and I will see you on Monday.